Okay, we are back, and now we're going to be talking about maximizing the evidence function. So in the previous section, we computed the evidence function. We got this kind of closed form expression for it in terms of alpha and beta, what we care about. And now we're going to try to maximize it in terms of alpha and beta, so then we can go back and plug it in. Okay, so let us first consider the maximization of P of t, the data given alpha and beta with respect to alpha. This can be done first by defining the following eigenvector equation. So this is going to be this is the precision of your likelihood on the weights. Always, whenever you see these things, always useful to do an eigen decomposition and switch coordinates because it decouples the variables. So we're going to do that eigen decomposition, we're going to get these eigenvalues. And why are we doing that? It's well because we're going to have if we go back to that expression, there's going to be a log. There's going to be a log of the determinant of a. And remember, a. What does a look like? So a is going to equal alpha times I plus beta phi t phi. And we want to, so its determinant is going to be the product of its eigenvalues. And so it's important, so it's useful to, well, crucial basically, to do this eigen decomposition. So we're going to do that, and we're going to write, alpha as u of u plus beta u, these are the lambdas, u transpose. So it's going to be an alpha I plus beta u transpose. And as far as the eigenvalues, as far as the determinants are concerned, you can just say, well, determinant of A is going to be equal to determinant of U times determinant of alpha I plus beta, and lambda is this diagonal matrix of all the eigenvalues, times determinant of U of t. These are these are orthonormal matrices, so they're just determinants are 1. They can also be -1, but if they're -1, well, then they'll both be -1. So either way, you can cancel them out. And you end up with this. And what is that? Well, this is just a very simple, it looks like a matrix as alpha plus lambda 1 all the way to alpha plus lambda, I guess, is it m? And so that's what we're going to get. And so the determinant is just going to be the product of alpha plus lambda I. Okay, so that's all that's about. All right, so that, and now we want to take its derivative with respect to alpha. Well, we've got the ln of this product, which then is going to become the sum of the lns of the individual components. And then we take a derivative, and we end up with this simple term. Okay, so the stationary points of 3.86. So where was 3.86 again? Yeah, this is which was our log marginal likelihood, or log evidence. So it's not the stationary points of this, stationary points of its gradient. Well, no, he's right. It is stationary points of that function. With respect to alpha, satisfy. So this was what we just got from our determinant term, and then there was a contribution from our penalizing of the weights, and then this was the normalizing constant. So now we have this kind of expression that we have for alpha, and the problem is alpha shows up here, it shows up here, it actually also shows up in the posterior mean, because you've got the posterior covariance multiplying some stuff, and that posterior covariance is alpha in it. So you're going to have and this comes up a lot where you care about some parameter, and it's kind of just tied up in all these various terms. So you have to resort to iterative methods, which is what we're going to do. So the first thing I'm going to do is multiply through by 2 alpha, and then rearrange, and then we obtain a particular equation. So there is the m multiplied by 2 alpha. The 2 alpha times this gives you the alpha mn transpose m of n, and then you've got an alpha showing up over this sum. And now we're going to actually define this term as gamma, and it's going to come up, and we're going to talk about it in the next section. It has a very interesting property. But the very first thing you should notice is that you can actually simplify this, because you can write m is going to, you can write this as sum of I equals 1 to m. This is just, I'm just writing what you can write m as, and this is going to then equal to, you can actually then write this as lambda plus alpha over lambda I plus alpha, right? And then now then when you add in this particular term, then you get, now I'm abusing notation a bit here, but lambda I plus alpha, and now you subtract the bottoms are the same, so you can subtract the alpha and alpha, and now you end up with gamma being equal to this expression. And we'll see in the next section why this is such a useful expression, but for now let's just live with it. So here is this gamma thing showing up, and it's got the alpha in it. Interpretation of the quantity will be discussed shortly. From 3.90, we see that the value of alpha that maximizes the marginal likelihood satisfies. So we're just going to rearrange things, right? So we've got we've got alpha m of n, mn transpose equals gamma. So we've got this ratio. Now note that this is an implicit equation solution for alpha, not only because gamma depends on alpha, but also because the mode of the posterior distribution itself depends on the choice of alpha. So we talked about that. We therefore adopt an iterative procedure. So this is a kind of a cool idea, an important idea that you should just have in your toolkit. And use find m of n, and then also value gamma, which is repeated until convergence. So these values are used to reestimate alpha, and then you just keep doing that. And again, when you do stuff like this, there's no guarantee that it will kind of converge to the right thing. Sometimes it will blow up. So it's not oh, we just equate these things. You actually have to check that they do converge. So yeah, but here we're just going to assume that everything works out. And I think on the whole, always assume that things are going to work out in the first pass. Don't worry too much about all these like little niggling or what if it doesn't converge, etc. But once you have something, okay, if your thing doesn't work, then obviously you have to go and have a look at what's not converging. And then if it does work, then it can be useful to be like, okay, well, what made it work? Did I just get lucky, or does it generally work? And then you can look at those aspects then. But I would recommend not worrying about things not converging, etc., until you really have to. Okay, note that because the matrix, so phi t phi is fixed. This is just our features, the overlaps of our features for our training data. We compute those eigenvalues once at the start, and then we'll simply multiply those by beta to obtain the lambda I. So yeah, so you don't need to keep evaluating the lambda i's. You can just do it once. Okay, it should be emphasized that the value of alpha has been determined purely by looking at the training data. In contrast to maximum likelihood methods, no independent data set is required in order to optimize the model complexity. Right? Again, so this is kind of an important point. So we don't have to again learn the W and then use it on some left out data to find its performance for the different values of alpha and then optimize that. We can just do it directly on the training data. Okay, so now let's do it. Let's do the maximization with respect to beta. Again, it's going to be the same thing, but I think the really cool thing was that was this, and it hadn't occurred to me, but remember that we've got a situation like b phi t phi is equal to times like the ith eigenvector is going to equal lambda I times that ith eigenvector. And so the main point is that this is fixed. So if you increase beta, then lambda I will increase. So the eigenvalues are linear in beta. And so that means that when we need to take their, like in principle, this could be kind of complicated, right? You're like, well, lambda I is this eigenvalue of this, of this matrix. I don't know how that necessarily behaves. Well, but because this, this part is going to be fixed, it's just some, some shape, some ellipse in space, and it's just scaling it. So, and you can think of these lambda i's as kind of related to the lengths of that ellipse. And so he's just saying that, look, these lambda i's are linear in beta. So d lambda I d beta I is just going to be like that. It's just going to be, it's the equation for the slope of a line. So that means that we can, so I'm going to actually highlight this. So it's kind of just a simple observation that allows us to kind of proceed here. So now we're going to take the derivative with respect to beta. Again, same as before, we've got this sum of the logs of the eigenvalues plus alpha. And now we just take the derivative. So now we get, 1 over lambda I plus alpha times d lambda I over d beta, which is just lambda I over beta, which then just gives us this expression. Okay, so yeah, and we just plug that in. So very simple once you have this idea. The stationary point of the marginal likelihood therefore satisfies, again, we've got this kind of normalizing constant. We've got, remember, there's a beta term outside of this goodness of fit term, so now just the beta disappears. And now we have gamma over 2 beta. And then after rearranging, we again we obtain, so we just move things around, and now we have this kind of expression. And again, we've got, we're in that situation where, because the beta is going to show up actually inside here, and it's actually going to show up with the gammas as well. So again, it becomes the same idea. So an implicit solution for beta can be solved by choosing an initial value for beta and then using this to calculate m of n and gamma, and then re-estimate beta using so on, so until convergence. And then, so let's just do that. We'll just highlight this. An implicit solution for beta. And then he says, look, in both these cases, we assume kind of what the other one was known. If both alpha and beta to be determined from the data, then their values can be re-estimated together after each update of gamma. So you have to, I haven't tried this. I haven't tried the other ones either, but I haven't checked this basically. But yeah, there is kind of an order in which you do it. So you first figure out gamma, and then you update the alphas and betas. Okay, cool. So again, you have to do, you have to kind of do these iterative things. Sometimes actually the order in which you do these iterations matter, so something to play around with. But in principle, you can do it, which is essentially what he's saying here. Okay, cool. So I think that is all I wanted to say about that section. Again, we're doing kind of very simple stuff here. We're just kind of computing gradients, setting them to 0, and then coming up with these iterative updates. So I think the iterative update aspect is kind of the most important thing to take away from this. It'll kind of, and it comes up quite frequently, so it's just something good to know about. And again, this trick, I hesitate to even call it a trick. It seems like quite obvious in hindsight, but a useful one which allowed us to get our expression for gamma over beta. Great. So next time we're going to talk about this gamma parameter, which is actually kind of has a very interesting interpretation. So hope to see you in that next section, where I think will be the last section on the evidence approximation. So hope to see you then.